In this session we will learn Small Computer System Interface, SCSI, and SCSI Architecture Model.
What is SCSI? SCSI stands for Small Computer System Interface, is a set of parallel interface standards developed by the American National Standards Institute, ANSI, for peripheral device attachment, namely disks drives, tape drives, printers, scanners to computer systems. SCSI model is supported by all major operating systems. SCSI inserts intelligence from the host to the interface circuits, making the system nearly self-managing. The current SCSI draft is SCSI 5, it is up to the OS vendors to implement it in the operating systems. SCSI includes both serial and parallel interfaces. SCSI objects communicate in a three-layer model. The highest level of abstraction is the SCSI application layer, SAL, where an initiator and a target are considered to communicate using SCSI commands sent via the SCSI application protocol. The SCSI transport protocol layer, STPL, defines how an initiator and a target need to communicate using a SCSI transport protocol. For example, transport protocols are SCSI parallel interface, fiber channel, serial attached SCSI, ISCSI, etc. The lowest level is the SCSI interconnect layer, SIL, defines how an initiator and a target communicate using an interconnect. This layer defines the services, signaling mechanism, and interconnect subsystem used for the physical transfer of data between an initiator to a target. SCSI layers can be split based on the implementation. The SCSI layers in the architecture can be implemented in the following way. Device-specific command sets layer. Shared command sets architectural model layer. Transport protocols layer. Physical interface layer. The device-specific command sets consists of commands specific to the connected device like hard disk, CD-ROMs, tape drive, controller commands, etc. The shared command set architectural model define a set of primary commands for all devices. The transport layer contains the protocols used, like FCP, InfiniBand, ISCSI, RDMA, SAS, etc. The physical interface is the physical media like fiber channel, Internet, SAS, SATA, InfiniBand, etc. Let us see how the data flows from application to the hardware. The application layer is responsible for generating any read/write I/O to a storage medium, hardware. Virtual file system acts as an abstraction layer over different types of actual file systems and presents the user application with unified file system calls. The actual file system interacts with block devices through generic block device layer. The generic block layer interacts to the device driver of the specific hardware, say SATA controller, AHCI, SAS controller, etc., where storage devices are connected. Let us see how a communication happens between a host and a storage device. A host, which is a SCSI initiator, storage device acts as a target. In storage systems, a SCSI initiator is the endpoint that initiates a SCSI session. It sends a SCSI command. The SCSI target receives and processes SCSI commands. The SCSI target waits for the commands from an initiator and provides required I/O data transfers. A target can have one or more logical unit numbers, LUN. A LUN is simply the number assigned to a logical unit, which is a SCSI protocol entity which can be addressed in the I/O operations. A LUN does not perform I/O by itself, but can perform on behalf of a specific LUN. In most cases, a LUN often represents a SCSI disk on which a host can perform a read and write operations. Now, let us see how a Linux SCSI subsystem is defined. The SCSI subsystem uses a three-layer design, namely SCSI upper layer, SCSI mid layer, SCSI low layer. SCSI upper layer supports the user-to-kernel interface by providing device nodes. Below are the names of the drivers used by SCSI upper layer. SD, SCSI disk. SR, SCSI CD-ROM. ST, SCSI tape. SG, SCSI generic. ch. SCSI Media Changer. SCSI mid-layer is the interface between SCSI upper layer and SCSI lower layers. The SD, SR, ST, SG, and CH are compiled as one driver mode called as SCSI_mod. SCSI low layer consists of HW-specific device drivers from different vendors like LSI SAS HBAs, Megarate HBAs etc., namely MPT3 SAS, Megarate_SAS. Now, let us see how a FreeBSD SCSI subsystem is defined. Common access method is specified for SCSI, providing round-robin prioritized transaction queuing, guaranteed transaction ordering even during error recovery, and a straightforward error recovery model that increases system robustness. Services are provided to both controller, SCSI to host adapter, and peripheral drivers that allow the system to take full advantage of advanced SCSI features while leveraging off of common code. Since the inception of the Small Computer System Interface Protocol, system programmers have faced several challenges in implementing software to communicate with SCSI devices. Although presented as a series of ANSI-ratified standards, extensive knowledge of standardized SCSI isn't sufficient to develop a robust and efficient SCSI subsystem. The interpretations of the SCSI standards are as varied as the vendors manufacturing SCSI devices, increasing the difficulty of designing a system that offers wide compatibility. Even without the specter of inconsistent vendor implementations, the challenges of reliable error recovery, efficient and fair use of bus and device resources, and exporting a clean API to applications removes the possibility of a simple SCSI implementation. Recognizing the difficulties inherent in supporting SCSI, the ANSI body developed the Common Access Method specification. CAM provides a formal description of the interfaces in a SCSI subsystem. These interfaces are tools that can be used to build a robust SCSI framework, but CAM offers few implementation guidelines and often lacks information on the common SCSI specification violations that must be tolerated to achieve interoperability. What is a good strategy for detecting non-compliant devices? What commands issued in what order should be used to probe for devices? What are the common problems encountered in supporting tagged queuing? These questions, and many more, are left for the implementer to answer. This paper seeks to document how one particular CAM implementation, written for the FreeBSD operating system, fills in the details missing from the formal CAM specification. A CAM system is composed of three basic components. At the highest level we find the peripheral drivers. Peripheral drivers serve as the interface between operating system services and CAM actions. A CAM system often provides peripheral drivers for tape, disk, CD-ROM, or other device types. Applications running on the system use generic operating system services, read, write, IOCTL, to access peripheral devices without needing to know the specific SCSI commands required to perform these actions. The transport layer is the ringmaster of the CAM subsystem is the transport layer, XPT. Charged with the important tasks of tracking peripheral, controller, and device presence, CAM system-wide resource management, and the routing of commands between the different CAM layers, the XPT is the source of most device-independent functionality in CAM. The XPT's role begins early in system startup when peripheral and controller drivers are attached, SCSI devices are probed, and the state of the CAM system recorded in the existing device table, EDT. Once the topography of the system is known, the XPT can assume its role as a router. The XPT uses its routing services to provide guaranteed delivery of transactions between peripheral driver instances and controller drivers. Even more critical to the system's proper functioning and performance is the XPT's task as a resource manager. The XPT schedules the allocation of device, controller, and XPT resources for all I/O transactions using a round-robin per priority level approach that guarantees fairness. Assignments. Explain in brief the SCSI layers and SAM models. With an example of Linux operating system, explain the SCSI layers. How is Windows operating system different from Linux with respect to SCSI? What is a store port driver and a mini port driver? Explain in brief how they work. Explain how a data flows from an application to a hard disk.
This is the end of the session. For any queries or more information, please log in to www.sbkmake.com. Thank you.